Today we'll be going over in this video exponential equations and applications involving exponential growth and decay. In order to be successful in this section, you will definitely need your logarithmic skills, so be sure to go back to that video if you need to. All right, let's begin. So to solve exponential equations, just like with logarithmic equations, we're going to be looking for two different patterns or varieties of equations that we'll encounter. The first type, again, is the simpler type, and that is when we have on one side of the equation a base raised to a power, like say b to the x power, and on the other side of the equation, the same base, b raised to some other power, let's say r. In that case, the only way that equation is truly equal, if that side equals the other side, is if the exponents are equal. So that's what we do. We simply set our exponents equal. For example, let's say I have 2 to the x power on one side equals 8. Now, the first thing to be careful with when you're reminding yourself how you solved exponential equations, which means x is in the exponent, right, is to remember this is very different to say 2 to the x than to say x to the second, right? We dealt with exponential graphs in a previous video. You might need to go back to that if you forgot about what these look like. These grow really rapidly because at every increase of one input x, you are multiplying the base by itself. You're multiplying by another factor of 2 over and over again. So this is really saying 2 multiplied by itself, how many times, rather, gives you 8? Well, 3, right? 2 to the third power is 8. But this is an easy example, but in reality, it can be much more complicated. And anytime we notice that we have a number on the other side that could be rewritten as that same base to a power, we're going to take that approach. So this is really 2 to the x equals 2 to the 3. 8 is really 2 to the third power, which now shows us the pattern we were looking for, which was namely that if the same base is on both sides set equal to each other, then the exponents must be equal. So in this case, x equals 3. Now some good news. These will get more complicated, I promise. Some good news though. Unlike logarithmic equations, which had very restricted inputs, remember the arguments of a logarithm had to always be, that's right, greater than 0. Exponential functions don't have any restrictions on the domain, right, on the inputs. Because our graphs, if you remember what an exponential graph looks like, if its base is bigger than 1, it's growth. This function models something like that, meaning that we're really saying any input is allowed, to the left forever and to the right forever. In this particular case, by answering x equals 3, what we've really said is the y value of 8 is achieved at the location x equals 3. So that's actually the interpretation of the answer visually on the graph. Okay. Now, when is this going to be useful to us? Well, later today, we'll be doing some really neat applications of exponential growth and decay, whether we're talking about when a population will reach a certain amount of money or people or items, or maybe we'll be talking about when a population or an amount of something, a substance, maybe a drug, okay, would actually be reduced to a certain level. We'll use something called the half-life when talking about radioactive decay or any substance that we consume. Okay, so that will be coming up later, but in both of those cases, one of the things you're going to be asked to find is how long will it take before this happens? And how long or time is typically your input. So we'll be solving for that x value or the t in those cases. Okay, let's look at our second possibility for an exponential equation. The second possibility, instead of the same base equaling the same base, is when we have an exponential part, like b to the x, equals something else, anything else. Okay? In that case, when we don't have the same base on both sides, we're going to need logarithms because that undoes an exponential function. We'll need our logarithms to bring down any powers. So we have to take the logarithm, whether it's the base 10 common log or base e natural log, that's up to you. I will recommend base e, the natural logarithm, because when you deal with financial applications or most exponential growth and decay models, you have base e involved, so natural log would be your better option in most cases. Well, when I've taken the natural log, for example, of b to the x, I also have to do it on the right, so that would be the natural log of r, which would mean that I'm allowed to now use my power rule from our previous video series. If you need to go back and watch log properties, that'll be helpful to you here, because that power can come right down in front. And now we simply have x times the natural log of our b equals the natural log of r. Well, what would you do to solve for x now that it's brought down? That's right, you would undo multiplication with division. And that's how we would get that the x would equal the natural log of r over the natural log of b in that case. Okay, well, let's apply that to an example here. Let me make some space. So in our example of an exponential equation here, we're dealing with something pretty complicated. Not as complicated as we'll get later, but pretty complicated. It says 2 times base 3 raised to the power of 4x minus 5 subtract 7 is supposed to equal 10. Again, graphically speaking, hopefully you know what this graph looks like, right? If you have a base 3 exponential graph, it's growing like the one above was, multiplying by a factor of 3 over and over again. But it's also been shifted left and right. It's also been stretched vertically by a factor of 2 and then moved down 7 units, right? So that graph, we have hopefully an idea of what it looks like. You could look in a graphing utility or desmos.com to visualize it. But we're really saying, does it ever happen that that graph, that exponential growth model, ever crosses the line y equals 10? In other words, when would I get an output of 10, right? At what x value? To solve this, I need to solve for what's in the exponent. So I would first need to isolate the exponent. A lot of people don't know where to start. That's where we start. We're going to isolate our exponent. So I'll first remove the 7 by adding it to the other side. So this would become twice 3 to the 4x minus 5 power equals 10 plus 7, which is 17. Now if I divide by 2 on both sides, I have to get rid of the 2 there before I've isolated the exponential function completely. I would now have 3 to the 4x minus 5 equals 17 over 2, or the decimal equivalent. At this point, I'm finally in the position to recognize, hopefully, one of these two situations that we described earlier. So which situation is this? Do I have a base equals to the same base on both sides, or don't I? No, I don't. There's no way to easily write 17 halves as 3 to some power like we did above. So in this situation, I would need to take the, that's right, log of both sides. I'll choose the natural log. So if I do that, I would have the natural log of this entire thing. But what's the purpose of that? It's to bring down the exponent. So I could save a step and do that at once. I'll recommend that, saving some handwriting here. So this would become 4x minus 5, all in parentheses, that's critical, times the natural log of 3, must equal the natural log of 17 halves. Again, if you had chosen to use the common log or any log base, as long as you do the same on both sides, that's perfectly fine, perfectly legal. Okay, now at this point you'd have some choices to make. One thing you'd want to notice is who you're solving for. I'm solving for x, and in this time there's only x living in one location. So that's really good news, since a linear equation means I just need to isolate that variable. So I have a choice here. I could either distribute the natural log of 3 to both of these terms, and then isolate x, which is an option for sure, or I could undo the multiplication right now and then move the 5 over and divide by 4. I'm going to take the second approach, but feel free to try both approaches and see in your calculator that you get the same result in the end. Okay? So by dividing by the natural log of 3, I would get 4x minus 5, living on the left side, equals the natural log of 17 halves, which is already present, now divided by the natural log of 3, right? Looks nasty. Now be careful here. Some students want to put those arguments back together. We can't do that, right? If we have a natural log over a natural log, the only way to combine those into a single log is to use the change of base formula. So if you really, really wanted to show off that you can combine those into a single logarithm, you can, but please do so correctly. It would have to be the log base 3 of 17 halves. Feel free, but most students probably shouldn't try that because you might make a mistake, just being honest. Okay, next what I'm actually going to do though is isolate x. So this is basic algebra skills here. Can we do that? Well, yeah, we would add 5, so let's do that. Adding 5 now gets rid of the 5 on this side. So now I just have, let me find my blue color again. Now I would just have the 4x here. So 4x equals the natural log of 17 halves over the natural log of 3, being careful to close parentheses around each argument. Otherwise, your calculator will give you the wrong answer, I promise. And then plus 5. Final step, we would divide either the entire answer in our calculator by 4 or divide each piece by 4. If you want to do it all in one short step, you just parentheses around the entire expression we just had, and then we would divide by 4. So dividing by 4 on both sides basically gives me x by itself. So now I have a very nasty looking answer. I grant you that, okay? We could write it in many, many different ways, especially if we had distributed instead of dividing here, or if we used the change of base formula to write log base 3 of 17/2. Lots of different ways to write this. But the key is that you can find an exact answer, which is correct. This one would be correct. And you could check that going back from where you started, making sure that you haven't made any errors. But also noticing that your actual approximation, when you put it in your technology, into your calculator, it will give you the same exact thing that you would have gotten any other way you've done the problem. So there's a variety of ways to do this, but they should all get you to the same place. In this case, the answer that you should get for x should be approximately 1.737 when you put it into your calculator. And let me know, you can always contact me if you have any trouble entering those into your calculator. I'd be happy to walk you through that. Okay, so we've done one example of each now. How do we solve How do we solve exponential equations? Well, either it's the same base on both sides, so we simply set the exponents equal and solve, or we have to take the logarithm of both sides in order to bring down any powers to the front and then isolate for our variable. They can get more complicated, but that's the general pattern. One of those two should happen. Okay, let's try some more practice. Here we go. Feel free at any time to pause and try this on your own and then come back to me. Okay, in example 1 it says, solve the exponential equation. 5 is being raised to the 1 minus x power, and it's equaling 2 to the x power. The question is solve. So we're asking you what input would make this true. In other words, we have two different exponential graphs here. It turns out one of them is growing and one of them is decaying. And we're asking you, is there a point of intersection? If so, where? What input would make this happen, this intersection happen? Okay, so without using technology, how would I do this algebraically? The first question I would ask myself is, self, do they have the same base? Nope, they don't. 5 and 2 are not the same base. Now, if this had been 5 and 25, then sure, I could make 25 5 squared, and I could go from there. But in this case, there's no way to turn a 5 into a 2 or vice versa. So we're going to begin with our second pattern, which was to take the log of both sides to bring our powers down. Let's do it. So if I do that, this is ln, or log, whichever you choose, of 5 to the 1 minus x equals ln of 2 to the x. Now the reason I do that is to bring down the powers. I always want to ask myself, why am I doing what I'm doing? Otherwise, if I just memorize something, I have no idea what I'm missing if I forget what's going on, right? It's better to understand what you're trying to do. I'm trying to bring my powers down, which is why I need logarithms. Okay, once I bring this power down, I have to remember that if there's more than one term in the power, to use parentheses for that power. So that's parentheses 1 minus x times the natural log of 5 equals x, because that power came down as well, times the natural log of 2. Now this problem looks a little familiar to me. It looks a lot like the last problem. However, there is a distinction here. Can you see what the difference is? That's right, x is in more than one place. I've had many students on tests give up right there. What? I have no idea what to do. Don't be that student, persist, okay? So how would I persist? I would persist by noticing that I could distribute ln 5 and then see what I have. Okay, well, let's do that. If I distribute ln 5, 1 times anything is itself, so that's just ln 5. And then negative x times ln 5 would be just that, negative x times ln 5. Equals on the other side, x times the natural log of 2. Now this is, again, great. If you've gotten that far, there's no reason to give up. You can do this, but maybe you haven't had a lot of experience doing something like this. I challenge that assumption, though, because I think you have. It just looks scary, to be honest, right? You don't like seeing a natural log of 5 next to an x. It freaks you out a little. But keep in mind, that's just a number, right? If I had negative 2x there instead, and if I had on the other side, instead of ln 2 times x, if I had 5x, you would know what to do. That's right. You would move all the x's to one side, and you would isolate x, wouldn't you? Exactly. So let's continue with what we know to do. Let's not give up. This would become, then, the natural log of 5 on one side, because that didn't have an x, so I'm going to leave it alone. And the terms that did have x, I'm combining. So on the right side, I'll have x times the natural log of 5 is now positive, since I've added it to both sides, plus the positive x that was already here, times the natural log of 2. Now you might think, okay, You got me a second ago. I agreed. I'll move it over. That's fine. But how in the world am I supposed to combine these two things? Good point. What we normally would have done is add the coefficients, right? So in this case, natural log of 5, that's how many copies of x we have, and natural log of 2. Well, if you add those two, that's how many copies of x you have. In other words, you could factor out the x. How many copies of x do I have? Natural log of 5 plus natural log of 2. That's how many copies of x I have. Okay, so that's all I did, is I factored out the x. That's a very common trick. Factor out x. If you're trying to solve for something, if you're trying to isolate it, you want to put it out aside in the front, okay? That is equal to the natural log of 5. Now, you could technically answer this question in one more step, because now x is simply by itself being multiplied by the sum of two natural logs. So I could do that. But if I was really trying to reduce the amount of writing I have to do, or entering in my calculator, because I might make a mistake because it's a lot to enter, I would recognize condensing whenever possible, as long as I can do that correctly. So feel free, again, to go back to our previous video if you need help reminding yourself how you can condense here. To condense two logarithms with the same base, here base e, that are being added together, what did we do with their arguments? That's right, we multiplied them. 5 times 2 is 10. So this could really be written as the natural log of 5 on this side is equal to x times the natural log of 10. Well, now there's just one more step. Can you see what it is? That's right, we had to divide by whatever is touching x. So if I divide by the natural log of 10 carefully, the natural log of 10 should cancel on the right side. Now I have x by itself. Namely, I'll clean that up a little bit. X is equal to the natural log of 5 divided by the natural log of 10, which I could put into my calculator, making sure to carefully close my parentheses, and I would get approximately 0.699 if I wanted to round to the nearest hundredth, or sorry, thousandth in that case. If, on the other hand, you were looking in the back of a textbook and you didn't see that answer, what do you think they did? That's right, they used the change of base formula. So remember that change of base formula we talked about in our last video? Log base b of argument a is really the natural log of the argument over the natural log of the base, or the common log of the argument over the common log of the base. Either one of those is appropriate, okay? This was called our change of base formula. Ooh, I cut off my head. That's impressive. Change of base formula. Okay, so remember that is the change of base formula. So in this situation, if you wanted to show off, you could say, or x is also known as log base 10, but isn't base 10 just log? Yep, of 5. So that would be an alternative way to write your answer, but as long as you get to this approximation, you have the right answer. Okay, so roughly 0.699 is the input that would make these two equations cross each other. All right, so we've done one example now. Again, try the next one on your own and then see how you did. All right, so before we jump into the next one, we're going to get there. It's going to be just like we've been doing, I promise. More exponential fun. But first, we're going to remind ourselves about applications involving finances and exponential growth and decay in general. So in general, anytime someone says that I have experienced something that is growing exponentially, whether it's the amount of cockroaches in your home or mold, in my case, when I bought my first house, that was very sad. Day 1, 6 mold spores. Day 2, 36. Very depressing. When you have exponential growth or exponential decay, and you want to generalize an equation that represents that situation, you could always use this formula. Just like with the line, you could always use y equals mx plus b, right? For an exponential growth model or decay model in that case. Whether it's growing or decaying, so growth would look something like that, right? Decay would look more like that. Okay, so we have growth or decay. In either case, we could use the model a of t, meaning the amount depends on t, which is time. Amount depends on time. It would equal the initial amount, so that's what a sub 0 is, the initial amount, times e, Euler's number, it's our natural base, right? Euler's number, which is about 2.71. It's that irrational constant, just like pi is irrational, raised to a product, k times t, where k is your growth or your decay rate. Now, it's growing if k is positive, and it's negative when it's decaying, okay? And t is your time, typically in years, but it could be in hours or days, so we have to pay attention to our model, what's going on. So we've already mentioned the first part. If k is positive, it's growing, and if k is negative, it's decaying. But another interesting application that uses this formula, we'll do it in an example in just a few moments, is half-life. What does it mean to talk about half-life? Well, it turns out that every radioactive substance and every chemical substance that you could possibly consume has a certain half-life. You could Google a half-life of caffeine. You could Google the half-life of Tylenol, right? You could Google the half-life of any radioactive material. A half-life is simply the amount of time it takes for 1/2 of the substance to remain. So for example, if you had a big chemical spill or a big, radioactive spill, if you spilled, let's say, 1,000 pounds of something, and something had a half-life of 20 years, if that item had a half-life of 20 years, then after 20 years, you would still have 500 pounds of that substance, because it's the time it takes for half of that substance to still remain. Okay. Now the good news is things that you consume typically have a much shorter half-life. We'll be talking about, I think, Tylenol coming up in a few minutes. Okay, so you'll want to be able to interpret half-life correctly. That'll be important. A couple other things. Two very special formulas that actually are just applications, they're more specific cases of exponential growth and decay, are banking interest. So if you put your money into a bank and you let it sit there for a while, the amount of money that you put in, the initial amount, is technically called the principal. It's the same thing. Interest can work for you or against you. So if you're not saving, maybe you get a loan, right? That's still the principal on your car or on your house, right? The principal is the initial amount. Now, why do we put it in this part of the formula here or here? The principal, or the initial amount, is in the front. It's the coefficient in front because at the original time when you make the deal, right, when it first begins, we say t is 0 at the initial amount. And if you were to put 0 for time in the exponent, anything to the 0 power is defined to be 1. And 1 times whatever is in front would be what's in front, right? Which means the principal, the amount in front, is what you start with. Okay, so it does make sense. It's not a made-up formula. It actually models the reality here. All right, so what's the difference between these two interest formulas? And there's also a simple interest formula, but right now we're talking about interest that is compounding. So if your interest is compounding or recalculating based on the amount of money in the bank at any given time, one of two things can happen. The money can be constantly growing. The interest can be constantly growing for you or against you, depending if you're saving or if you borrowed. Or it could be only recalculating or recompounding every so often, right? So n number of times per year. And that's the n that you see in the second formula there. R over n, nt power. So for example, if you put your money into a bank and you asked, how does my interest compound? How often does it compound? They could say quarterly, for example. Well, how many quarters are in a year? Well, kind of think of a dollar. How many quarters are in a dollar? 4, right? How many quarters are in a basketball game? 4. Okay, so on. So 4 quarters in a year, meaning every 3 months. N would be 4 in that case, right? Or if they said your money, your interest rather, will compound daily. Turns out they won't use the 365, but rather a banker's year of 360, because they're saying on average each month has 30 days in it. 30 times 12 is 360. So it's a little bit easier for them, but they also cheat you out of 5 days of interest, so just be aware of that. So daily would be n is 360. Other than that, they could talk about, weekly, 52. All right, so there's different options there for n. The best one for you, if you're talking about saving money, would be continuously, right? You'd like your interest to compound all the time, but if you were talking about something that you borrowed, you'd want it to be slower, right? That interest hopefully would be slower for you. Now, what is R? R is your interest rate. It's just like the growth rate K in the first equation, but it's an interest rate, so it's going to be a decimal. So if you have 5% interest, R is 0.05, for example. All right, so let's see how we would apply one of these formulas to a real-life situation. It says, for example, if you had $1,000 to deposit into an account, paying 5% interest, could we determine how long it would take to accumulate $5,000, assuming that interest is compounded continuously? Oh, so this is the nice case. My money is always growing. Okay. All right, so in this situation, I'm going to go through it carefully, and just a little tip for word problems. A lot of people have phobias when it comes to word problems, but at the same time, I hear a lot of people say, when am I ever going to use math in real life? Okay, this is your answer. Word problems are, yes, contrived examples from real life. And so what you want to do anytime you're encountering a word problem is not run away, but rather to ask yourself, what's the type of situation I'm talking about? Because there's probably a formula that models this. Once you've discussed that with yourself or someone else, maybe you consult the internet and find a formula that looks like it models your situation, then you want to fit into the formula whatever information you have, and then find whatever information you don't. That's it. That's all word problems are. Whether it's a math class, a physics class, it's always the same idea. Okay, so let's see what we know. We know that we're having interest, so we use an interest formula, that's compounding, so a compound interest formula, that's one of these two. But how is it compounding? It's compounding continuously, so we're going to use the first one. A would equal my principal P times e to the RT, right? That would be my compound continuous formula. So the word continuous was really critical there. It told me which formula to use. Once I have my model in front of me, I'm going to fit it with what I know. I know that I'm starting with $1,000 as my initial deposit. And I'm not going to put any more money in. There's other formulas if you do add money, by the way. But we're not doing that. We're just going to put our money in, maybe it's your refund check, and we're going to forget about it, okay? So I know that's hard, but let's try to forget about the money. We're going to put $1,000 in the bank and forget about it. Well, that must be my principal. So my formula now has 1,000 where P used to be. What else do I know? Well, they give me 5% interest, okay? How often? Continuously. So R is what? 0.05, very good. So R equals 0.05, P equals 1,000. They say how long? So we are looking for time. So we want T, because they said how long. You got to know what you're looking for, otherwise you're just wandering around in a formula with nowhere to go. We are looking for T. How long? Okay, that's what we are after. Would it take to accumulate $5,000? So what is that amount? Well, that's the accumulated amount. So A is 5,000. What else did they tell me? Well, it's compounded continuously. So I have everything I need. Plugging in what I have then, let's see what we could rewrite this as. A is now 5,000. P is known to be 1,000. E is Euler's number, so it's still E. My interest rate is 0.05, and T is what I'm solving for. Okay, so where do I begin? Well, we've done examples like this earlier today. Feel free to pause it and try it on your own, right? What we did earlier, though, is we isolated the exponential part. So that's the first step, isolate the exponential part. To do that, I would have to undo multiplication. Now, I see students here make all kinds of arithmetic errors. The opposite of multiplication is division. I've seen students subtract 1,000 right here, and that's very sad, right? That does not undo multiplication. So we're instead going to divide both sides by 1,000. And if I do that, 5,000 divided by 1,000 is really 5. Well, that's quite nice. We're trying to be kind to you here. So 5 equals e to the 0.05, that was my interest rate, times time. Okay, where do I go from here, right? Well, I would like to solve for t, which is in the exponent. In order to solve for an exponent, I need to take the natural log of both sides. Well done. So let's take a look at what that would mean. Taking the natural log on the left, that's the natural log of 5. And on the right, that would be the natural log of e to the 0.05t. Okay. What does that mean? Well, a couple of things. You could bring 0.05t down in front and then recognize that you have a natural log whose base is e and whose argument is e. Remember, anytime you have a log base b of b, that is equal to what? 1. So in this case, natural log of e, since its base is e, equals 1. So that's kind of interesting. Okay? Or you could also remember that if you have a log whose base is b and whose argument is b to some power m, isn't it just the power? And that saves you a lot more time, because in this situation, that's what we have here. We have a log whose base is e, whose argument is e to the 0.05t, which means we just have the power there. So this is really quite nice. What we have now on the left is natural log of 5, and on the right is just 0.05t. And now hopefully you can solve this linear equation, right? Undo multiplication with division, you'll get that the natural log of 5 divided by 0.05 is your t. Okay, so that's your exact answer. Or 1/2 ln5 would also work, right? The approximate answer, when you put this in technology, let me find it here, your t should be roughly, to the nearest decimal, nearest tenth, 32.2. So that was in years, right? So roughly 32, over 32 years have to go by for your $1,000 deposit to grow to an accumulated amount of $5,000, assuming that you haven't touched it for 32 years and your interest rate was 5%. Now, if you don't want to wait that long, there are things you could do. You could shop around for a higher interest rate. You could put it into a stock market instead. Or Another thing you could do is you could add money, okay? But the best option would be to initially deposit more money or to have a lot of time to watch it grow. Okay, so we're going to do more examples like this in just a moment, but if you need to pause and go through this one again, feel free, because the setup is really the hardest part for most students and word problems. Example 2 says, Sue took 500 milligrams of Tylenol at 8 a.m. Tylenol is known to have a half-life, it tells us, of 3 hours. When will only 25 milligrams remain in Sue's system? Okay, so there's a lot here. One thing that you don't see anywhere in this word problem, by the way, is the word exponential. You don't see it anywhere. But anytime you're given the word half-life, you want to think exponential decay. Okay, so that is something that you will need to bring to the table here, a knowledge of what half-life is talking about, right? Half-life is this situation where we're dealing with an exponential decay model, and initially at t equals 0, you start off with a certain amount in your system, in this case, Tylenol, and over time, it gets smaller and smaller, sorry, should be a dot there, smaller and smaller and smaller. Less and less is in your system over time, right? Now, it's given us the half-life, so that's important, but let's remember what an exponential model would look like, right? We had it on our last slide. In general, if it's not a financial application, we're going to use as our exponential model the amount depending on time t equals a sub 0, the initial amount, times e to the kt. So in this situation, let's see what we know so far. Well, we know how much she took initially, right? We know that she started with 500 milligrams at 8 a.m. Now you might be wondering, why did they give me 8 a.m.? Well, that's her starting time. So we know initially at time t equals 0, that's referring to 8 a.m., okay? So this is the original situation when time t equals 0. So at t equals 0, the amount at t equaling 0 is given to us as 500. Well, we could plug that in, right? And if you put in 0 here, what would that mean to us? Well, e to the 0 power is 1, so you would have 1 times a sub 0, which would make a sub 0 500. You can also just memorize that if you prefer, that 500 being the initial amount is actually your a sub 0. A sub 0 is always your initial amount. Okay. You'll see that in physics as well. Anytime you have the subscript 0, that means initially what's happening. All right, so at the very least, we could rewrite this formula as the amount depends on time t, and it equals 500 times base e to the kt. So you have one of the constants solved for. You know what a sub 0 is. But the other constant is really important. That's your growth rate. In the last problem, it was your interest rate that was provided to you. But this time, they're not providing the decay rate to us, are they? So what we need to do is we need to use our half-life to figure out k. So we're going to use my half-life to find k. So let's see how that would work. To use my half-life to find k, what do we know? Well, we know after 3 hours, so when t is 3, the amount when t is 3 is equal to how much? Well, let's think about it. It's not 25. That's the question. The question wants to know when will she only have 25 milligrams left in her system. We know, though, because it's half-life, that after that amount of time, she should have half of the initial amount, right? So you could write half times a sub 0, or you could just say, I know she started with 500, didn't she? So half of 500. In other words, half of 500 is just 250. Okay, so there is a shortcut to this, and you'll see it in a moment. But based on that information, if you know that at 3 hours, she has 250 milligrams in her system, so that's like right here, at 2 hours, she has 250 milligrams. Initially, oops, I don't know why I wrote 2550. That's interesting. Let's get rid of that. Okay. So we know initially, she started off here at 500 at 0, and 2 hours, sorry, 3, I don't know why I wrote it 2. Sorry about that, guys. Here we go, 3. 3 hours later, she only has 250 left in her system. So that's the situation so far that we know. Well, we're going to use that to find k, and let's see how that would look. So up here, perhaps, let's do it. We're going to say, well, I know that the amount becomes 250. The initial amount is going to stay the same in these problems. They'll give it to you. You keep it constant, times e to the kt. But this time, t is actually, do you see what it is? That's right, t is 3 in this case, and we're dealing with the half-life. And we can now solve for t. It's exactly the same as the past few examples now. We isolate the exponential part, and we're going to solve for k. So see last example if you need help doing that. See last example. But let me just save some time and tell you what you should be getting here after you take time to find that for yourself. In this example, your k should end up being the natural log of 0.5 divided by 3. Okay, so try to get that on your own and see if you can verify that. Now, if you were to put that in your calculator right now, you should be getting approximately negative 0.231. And that should be making a little bit of sense right now because it's negative, right? And if you know k is negative, it should be decaying, which is exactly what half-life is telling us. So we're going to actually use our exact answer. We're going to hold off on the rounded one, okay? So we're not going to actually use the rounded one. I wanted you to see what it looks like, but don't use it because it's been cut off too soon. We don't want to round until the very end. What I would do instead is I would use whatever my calculator has as my k, okay? Finally, I'm ready to answer the question now. We want to know so we're looking for t, right? What is t when we end up with the amount of 25 milligrams? So if I put 25 milligrams should equal the initial amount, 500, times e to the k, where k was the natural log of 0.5 all over 3, times t. Okay, we're looking for t. I'll get you started here, but again, you should be able to do this just like the last one. What you would want to do is isolate the exponential part by dividing both sides by 500. So if you take 25 and divide it by 500, you can reduce that, of course. You could also get the decimal, okay? So if you reduce that, you're getting 1 over 20. So I'll just rewrite it to make it prettier. Is equal to e to the natural log of 0.5 over 3 times t. And then to solve this, you'll do the same thing you did in the previous one, right? You're going to be taking the natural log of both sides, so natural log of 1 over 20. But taking the natural log of e to a power is just the power, right? We learned that in our last example. So this is just the natural log 0.5 over 3 times t. Now, if you're wondering what in the world would I do next, that's really scary. That's okay, deep breath. These are going to get much worse. All right, what we would do next is say to undo multiplication, we would use division typically, right? But division here, if you're talking about multiplying by a fraction, dividing would be multiplying by its reciprocal. So really you'd be multiplying by the reciprocal here, 3 over ln 0.5, which would mean on this side we'd have 3 on top and we'd have ln of 0.5. I don't know why I put that there. Let's put it like that. Okay, ln of 0.5 on the bottom. And these would cancel now. So t is actually equal to parentheses for the entire numerator, 3 times the natural log, parentheses, of the argument, 1 over 20, close both parentheses, all divided by the natural log of parentheses, the argument 0.5, close parentheses. Okay. Entering that correctly into your calculator can be difficult if you don't use the parentheses in the right places. Remembering there's many ways to write the same thing. You could use the change of base formula after bringing that 3 up as a power. So there's lots of ways you could write this. But in the end, when you put that in technology, you should be getting roughly 12.966 hours. And again, feel free to contact me if you need any help with your calculators. Okay? The important thing is to be able to apply this information to real life. So here we are doing that. We now know that she can expect to only have 25 milligrams of Tylenol left in her system 13 hours after taking her initial amount. So if you think, okay, what would 12 hours have been? 8 a.m. to 8 p.m. So this is 13 hours roughly. So roughly, approximately at 9 p.m. that same day. So around 9 p.m. we can expect her to have that amount left. So maybe she can pass a drug test or something. So anyway, that is an example of using exponential growth and decay to solve a real-life half-life problem in this case. Okay, the last couple things we're going to do, I promise we're almost done. I know there's a lot in this video. But the last thing we're going to do now is we're going to apply exponential and logarithmic functions to inequalities. And we've done this before. In your previous chapters, we studied polynomials, right? And we studied rational functions and their inequalities. But we remembered that if we knew how to sketch their graphs, we knew how to answer inequalities. So we're going to apply the same thing to logarithms and exponentials to finish off this video. Here we go. So when solving an exponential or a logarithmic inequality, it will look at first like an equation. The only difference will be the inequality symbol. So for example, I have down here log base 2 of 5x minus 4 as your argument, and that whole logarithm is greater than 4. So again, if you were to graph this, what we'd be looking for is when are my outputs bigger than 4? For what inputs are my outputs greater than 4? For what x values are my y values bigger than 4? Well, another way of doing this, if you remembered from our previous chapters when dealing with inequalities, was to first move everything to the left side, to graph it, and then answer the question as to when I'm above or below the x-axis, above or below y equals 0. So let's begin with step 1 here by noticing that we can move 4 to the other side and have log base 2 of parentheses 5x minus 4, close parentheses. Moving the 4 to the other side would make this negative 4, and now it's all supposed to be greater than 0. So that's what we're trying to actually graph. Okay, so that is our goal, to graph that side, the left side. So in step 2 here, that's where we begin our graph. We're going to graph this function, but when we graph this function like y equals log base 2 of 5x minus 4 in parentheses minus 4, when we graph this function, we're going to only care about the intercepts, especially the x-intercepts, and the asymptotes. In this case, a vertical asymptote, because it's a logarithmic graph, not an exponential one. So let's remind ourselves how to get an x-intercept, for example. Any x-intercepts are gotten by doing what? That's right, letting y equal 0. So if you let y equal 0, you'd have 0 equals log base 2 of 5x minus 4, close parentheses, minus 4. Okay, the reason we're doing this at the end of this chapter is because we needed all of this information about how to solve logarithmic equations, didn't we? So take a moment, pause the video if you need to, and solve this logarithmic equation. It's just like what we did in our last video. All right, so to do that, what did you do? That's right, you'd move the 4 to the other side. So you'd have 4 equals log base 2 of 5x minus 4. Now, this was that variety where you have a log equals a number. What did we do back in the last video to solve this type of equation? That's right, we switch back to exponential form. So the base is 2, 2 to the 4th power must equal the argument, 5x minus 4. And then we can solve that nicely, I hope. 2 to the 4th power is just 16. Is supposed to equal the linear equation 5x minus 4. Take a moment and solve. All right, what'd you get? Well, 5x would equal 20, wouldn't it? So if you have 20 equals 5x, what was x? Yeah, x is 4. So let's just erase that and make some space. So x must equal 4. That is my x-intercept, the only x-intercept. So let's put that on the graph. At x equals 4, so 1, 2, 3, 4, that is an x-intercept. Okay, once you have the x-intercept on the graph, we also want the asymptote, and then we want to draw a quick sketch. Well, is this logarithmic growth or decay? Well, look at your base. Base 2 meaning that this was logarithmic growth. If it's bigger than 1, if your base is bigger than 1, it's growing. So this graph would have looked something like this originally, okay, with a vertical asymptote originally at x equals 0. Well, if your graph is shifted, to find out the location of the new vertical asymptote, you simply would take your argument, and the argument in this case was 5x minus 4, right? So take my argument 5x minus 4, and I would say it has to equal 0 because the original asymptote was x equals 0, which was the original argument of y equals log base 2 of x, right? It had a vertical asymptote here at x equals 0. So if we've shifted the graph, it looks like horizontally a little bit. I know we have that 5 in front, so it can be a little strange. Let's see what's happened. Well, 5x would equal 4, so that x would equal 4 over 5. And 4 over 5 is also known as 0.8, so almost 1. That's the location of my vertical asymptote. So at almost 1, that's where I'm going to put my nice vertical asymptote. So my vertical asymptote at x equals 4/5, or 0.8. Okay. And we know it's logarithmically growing. It's also been moved down 4 if you're curious. But for our purposes, we just need to know the x-intercept, the vertical asymptote, and how it's growing. Okay, so we grow something like this. So we have our sketch. Now what we're interested in for step 3, finally, let's find out another color here. For step 3, we're just going to answer a simple question. And the question is, when is my graph below, above, or on the x-axis? In this case, which inequality arrow do I have? I have greater than 0. So I want to know in step 3 here, when is my graph, because it's greater than 0, when is my graph above the x-axis? That's the question. What inputs would give me outputs which are greater than 0? Well, it would be after the x-intercept, wouldn't it? It would be this region. In other words, my solution would be inputs to the right of 4, or parentheses 4, comma, infinity. So that would be my solution to this inequality. Okay, now in the last example, we're going to do another one, but it won't be logarithmic, it will be exponential. So feel free to pause and try these 3 steps, but on the exponential version. Okay, let's see how you did. We have example 3, solve the inequality. 4 times 2 to the x is less than or equal to 32. Write your solution in interval notation. What was our first step? Well, we wanted to get 0 on one side, on the left, 0 on the right, everything else on the left. So this would be 4 times 2 to the x is less than or equal to 32. But if I move 32 to the other side, that would mean I subtracted it, wouldn't it? It would. So what does this mean? Well, now I know what I'm graphing. So let's get another color. How about red? I'm going to be graphing what's on the left side here. So I would like to graph y equals 4 times 2 to the x minus 32. What kind of graph is this? That's right, it's exponential, right? And is it exponential growth or decay? Look at your base. If the base is bigger than 1, it's exponential growth in this case. So originally, if I was just graphing y equals 2 to the x, it would look something like this, wouldn't it? With the horizontal asymptote at y equals 0. You can go back to our first video series in the series from this chapter if you need help graphing those again, okay? But to graph this, what I would need to do at the very least is find any x-intercepts. And again, how do we always do that? That's right, we let y equal 0 and solve for x. So letting y equal 0 here, we get 0 equals 4 times 2 to the x minus 32. Okay, this is an exponential equation, just like the ones in this video so far. So again, you can pause it if you haven't already done so and solve for me and see how you did. Okay, moving the 32 over, let's see what happened. 32 would equal 4 times 2 to the x, which would then mean I need to isolate the exponential part, don't I? 32 divides by 4 nicely. What is it? It's just 8. Good job. Hey, this is really a nice, cute little problem now. 8 equals 2 to the x. We started with that at the very beginning of the video, didn't we? That's the same base on both sides. 2 to the 3rd power equals 2 to the x. Now, sometimes you've done so many more difficult problems that you don't even see the easy stuff when it's in front of you, right? So you might just take the natural log of both sides and you'll get the answer eventually. But when possible, we take shortcuts, don't we? So x equals 3 would be my one and only x-intercept. Let's put that on the graph. At 3 there. So what does that mean? Well, that's an x-intercept. We need to get a basic sketch. So let's get our horizontal asymptote. Now the horizontal asymptote is going to be, let's look at this, we see it's down 32 units, right? So way down here somewhere at y equals negative 32, that's our horizontal asymptote. So we know that's happening. If you really wanted to get a y-intercept, you could, to get a better sketch, right? For the y-intercept in this case, let x be 0. And that would mean that you'd have y equals 4 times 2 to the 0 power minus 32. What would that mean? Well, 2 to the 0 is 1. 4 times 1 is 4. And 4 minus 32, what do we get there? 2 to the 0 is 1. 1 times 4 is 4. 4 minus 32, oh my, that's negative 28. Wow. So that's my y-intercept. So way down here somewhere at negative 28, it's finally going to cross the y-axis. It was exponential growth, so it was looking something like, oopsies, something like this. Okay, so you got a basic sketch on your hands. You needed an intercept, you needed asymptotes, and you needed to know how it grew. And now you can answer the final question for step 3. Final question for step 3. We wanted to know when we are less than or equal to 0. In other words, when are we on or below the x-axis? What does that mean? Well, that's going to be on it at the x-intercept and below it to the left of 3, the x-intercept. In other words, any value on or left of negative 3, negative infinity until the x-intercept 3 with the bracket. All right, that's a lot of content in this video, so it's up to you now to make this your own. So go practice, and if you have any questions, feel free to reach out. Remember, math is not a spectator sport. Good luck.